So here's a table that allows you to see the Butterworth prototype solutions. And one thing I want you to notice here is basically the G2 value or the G3 value. In general, I want you to notice the Gn+1 value, because that's basically the last element and is basically the load. Right? So what that table means is that if you choose a first order basically filter, then the last element, which will be your load, should be equal to 1 ohm. If you choose a second order filter, then you will basically have a series L or a shunt C, but the last element right here, your G3 in this case, is the load and is again 1 ohm. So what is interesting to see here is regardless of whether you have even or odd order, the load is always equal to 1 ohm, and that's really convenient because that means that both your source and the loads have the same normalized impedance of 1 ohm. So when you scale things up to different impedances, no matter what, you will basically scale both of them at the same time, and it's simply a very convenient thing to have. Here is the attenuation for different orders of Butterworth, and here is plotted as omega minus omega c minus 1, omega divided by omega c minus 1. So the way you use this type of a graph is you choose your cutoff frequency, and then you choose the frequency that is slightly above or higher depending on what you want. So for example, the requirement might say that at 20% higher frequency that your cutoff, you must have a rejection of, let's say, 30 dB. So in that case, you will basically go 20% higher than the cutoff. You will basically be right here. You need a specific rejection. So let's say it's 10 dB. And so that means that any filter basically above, let's say, order 5 or something will work for you. Or if you basically go for twice as much as the cutoff here, you need a requirement of 40 dB or whatever the case might be, and that's how you select the order. It's very similar things happen for Chebyshev. The equations are slightly more messy, I guess, messier, but nothing really difficult, can be programmed very quickly. However, what I do want to point your attention on the Chebyshev side is that this nice property of having the G naught, the source resistance, being equal to Gn+1 is not necessarily true. In fact, the reason for that is because for a Chebyshev polynomial, you have a ripple. So within your passband, your Chebyshev might actually look like this, right? And then start rejecting. Or, and I'll do another example here. Whoops. Showing only the passband. Or you may have something like this. So either, in other words, you can start from 1, or you might start from less than 1, which will be the ripple. So it turns out that if you choose an odd order polynomial, 3, 5, 7, whatever, your S to 1 at 0 frequency will be equal to 1. So this is the case for an odd order. And in that case, your load will actually be the same as your source impedance. But if you choose the even polynomial, then your S to 1 actually starts on the bottom of the ripple. And in that case, your Gn+1, which is again the load impedance, the load resistance, is not actually equal to G naught, 1 ohm. It actually has a value that depends on the ripple epsilon. So let's see that in the table format. So here you can see, for example, for n is equal to 3, we have the load to be equal to 1, but for n equal to 4, my load is almost twice as much. Right now, this might appear as an inconvenience, and it could be if you make a simple brute force lumped element realization like the one we're talking about here. But as you will see pretty soon, that's not that big of a deal. Also, you will find many different tables for different levels of ripple. This is a case for 0.5 and 3 dB. Here I basically copied 2 tables that you will find often in books. But to be quite honest with you, these are not useful tables in the sense that no one designs a Chebyshev for 3 dB. In fact, even half a dB ripple is pretty high. Most people will design 0.1 to 0.2 dB ripple these days. But nevertheless, I've given you the equations so you can basically very quickly derive the equations that you need and the elements that you need. So these tables, these graphs that you see here are working in a very similar way. You just select the order of the filter based on the needed attenuation. And so this is something, for example, that you will do in the project for this class.